Chapter 4b, Transformer Clock System Vector Nomenclature. The main purpose of power transformers in a system is to change voltage levels. That is, to convert the magnitude of the voltage either up or down depending on the requirements. For example, distribution utilities may want to take the high voltage transmission levels of 500, 230, 115 kV to voltage levels, say 25 kV, for ease of retail sale to customers. Or an independent power producer may want to step the generation voltage up to the level that could be connected to the transmission utility. If we were dealing with a single phase quantity, the choice of connections would be a simple matter of using the correct turns ratio. However, when dealing with three-phase quantities, which are the ideal for economical transmission and distribution, not only the turns ratio has to be taken into consideration, but also the variety and permeability of connections. That is why transformer clock system vector nomenclature was developed. With every power transformer installation, we will have a primary system connected to the primary side of the transformer and a secondary system connected to the secondary side of the transformer. For simplicity's sake, we can assume that the primary side is energized by a three-phase balanced set of voltages rotating counterclockwise and having a phasor separation of 120 degrees. Depending on the transformer connections, the secondary voltages can either be rotating in a clockwise or a counterclockwise direction. Assuming, however, that we are still dealing with a balanced system, the secondary voltages are equal in magnitude and 120 degrees apart, but may lead or lag the associated primary voltages. But in all systems, it is desired to have both primary and secondary systems rotating in the same direction, and that as a standard is usually counterclockwise. This, of course, goes for the phase-to-phase voltages as well, specifically when we're dealing with a delta-delta connection. Take, for example, a star-star or a Y-Y connected transformer. We have already looked at this connection, and it is fairly straightforward. However, if we reverse the connections of each of the secondary windings, it would still be Y-Y connected, but certainly the secondary phasors would have to be different. As is the case for a delta-delta connected transformer. Again, we have already looked at this connection, and it too seems fairly straightforward. However, once again, if we reverse the connections of each secondary winding, it would still be delta-delta connected, but certainly the secondary phasors would have to be different. Another example would be the star-delta connected transformer, which we also have studied. And we used these secondary connections, as you see in the diagram. We could have just as easily used the secondary windings connections that you see here now, and it would still be a star-delta transformer. So how do we simply convey the configuration along with the connections? The answer is transformer clock system vector nomenclature. As its name suggests, we use the clock face as a reference for relating the secondary voltage to the primary voltage. The digits 0, 1, 2, 3, 4, etc. relate to the phase displacement between the high voltage and the low voltage windings using the clock face notation. The phasor representing the high voltage winding is taken as a reference and set at 12 o'clock. It is assumed that the phasors are rotating in a counterclockwise rotation. We use the hour indicator as the indicating phase displacement angle. Low voltage lags the high voltage by 30 degrees in this instance. Because there are 12 hours on the clock and a circle consists of 360 degrees, each hour represents 30 degrees. For example, 2 o'clock is 60 degrees, 3 o'clock is 90 degrees, 4 o'clock is 120, 5 is 150, 6 o'clock is 180, 7 is 210, 8 o'clock is 240, 9 o'clock is 270, 10 is 300, 11 is 330, and 360 puts us back at the 12 o'clock position. This can also be referenced as 0 degrees, so it could be 0. We're now going to look at some examples of the workings of a clock face nomenclature, and I'm going to start with a YY connected transformer. And we've seen this connection before, and believe it or not, there are 6 different ways to connect up the secondary windings of this transformer. Number 1, starting with our previously studied connection, the secondary phasors would look like this, showing that the secondary voltages are in phase with the respective primary voltages. Using just one set of phasors, the red one in this case, the clock system of vector nomenclature would tell us that there is 0 degree displacement from the secondary to the primary windings. The clock system nomenclature would be then YY0. We could have also said YY360, but normally we just choose 0 instead of 360. It's much easier to write on a piece of paper, I guess. Notice also that the primary side is designated with a capital Y, where the secondary is designated with a lowercase y, followed by the displacement, which is 0. The second YY connection would look like this. The red winding X1 terminal is connected to the secondary blue phase bus. The white winding X1 terminal is connected to the secondary red phase bus. The blue winding X1 terminal is connected to the secondary white phase bus. And all of the X2 winding terminals are connected together to form a secondary neutral. The secondary phasors look like this, showing the secondary voltages are 120 degrees lagging their respective primary voltages. Again, just using the red phase vectors, the clock system of vector nomenclature would tell us that there is a 120 degree displacement of the secondary voltage. The clock system nomenclature would be YY4. For the third connection, the YY connections would look like this. The red winding X1 terminal is connected to the secondary white phase bus. The white winding X1 terminal is connected to the secondary blue phase bus, and the blue winding X1 terminal is connected to the secondary red phase bus. And all of the X2 terminals are connected together to form a secondary neutral. The secondary phasors look like this, showing that the secondary voltages are 120 degrees leading their respective primary voltages. Again, just using red phase vectors, the clock system of vector nomenclature would tell us that there is a 120 degree displacement leading of the secondary voltage. The clock system nomenclature would be YY8. The fourth connection of the YY configuration would look like this. The X1 terminals are connected together this time to form the secondary neutral, and the X2 winding terminals are connected to their respective red, white, and blue phases on the secondary bus. The secondary phasors would look like this, showing that in the secondary, voltages are 180 degrees out of phase with the respective primary voltages. The clock system of vector nomenclature would tell us that there is a 180 degree displacement of the secondary voltage. The clock system would say YY6. For the fifth connection of the YY configuration, the X1 terminals again would be connected together to form a secondary neutral. The red winding X2 terminal is connected to the secondary blue phase bus, the white winding X2 terminal is connected to the secondary red phase bus, and the blue winding X2 terminal is connected to the secondary white phase bus. The secondary phasors would look like this, showing that in the secondary, voltages are 60 degrees leading their respective primary voltages. The clock system would tell us that there is a 60 degree leading displacement of the secondary voltage, meaning the clock system nomenclature would be YY10. The sixth and final connection of a YY configuration would look like this. The X1 terminals again would be connected together to form a secondary neutral, while the red winding X2 terminal is connected to the white phase bus, the white X2 terminal is connected to the blue phase bus, the blue X2 terminal is connected to the red phase bus. The secondary phasors would look like this, showing that the secondary voltages are 60 degrees lagging the respective primary voltages. The clock system of vector nomenclature would tell us that there is a 60 degree displacement in the secondary voltages, and the clock system would then read YY2. Now let's look at a delta to delta configuration. We have already studied this configuration with the primary windings connected like this. It would produce these phase-to-phase voltages on the primary side. With the secondary windings connected in a similar fashion, it would produce voltages that would look like this. The red to white primary voltage is in phase with the secondary red to white voltage. The white to blue is in phase with the white to blue, and the blue to red is in phase with the blue to red, primary to secondary, of course. In general terms, we might say that the primary is in phase with the secondary. So the clock face nomenclature would tell us that the primary is in phase with the secondary, such that this delta-delta connection would be DD0. Now this delta-delta connection could have a variation of 6 different secondary connections if you wanted to go through them all. I'm not going to do this at this point because we've already done that exercise with a star-star connection. However, I will look at one, which is fairly simple. What would happen if we reversed the secondary terminals of this delta-delta connection? The phasors of the secondary would be reversed, giving us this phasor configuration, meaning that the red to white primary voltage is 180 degrees out of phase with the red to white secondary. The white to blue is 180 degrees out of phase with the white to blue primary to secondary, as is the blue to red primary 180 degrees out of phase with the blue to red secondary. And in general terms, we would say that the primary is 180 degrees out of phase with the secondary. The clock face nomenclature would then be DD6, indicating this 180 degree phase shift. For the Y-delta connection, we have been through this exercise before, and we saw that the red to white secondary is in phase with the red to neutral primary, and that the red to white primary voltage is leading the red to neutral primary voltage by 30 degrees, meaning that the red to white primary voltage is leading the secondary red to white voltage by 30 degrees. And again, in general terms, we can say that the secondary is lagging the primary by 30 degrees. The clock face nomenclature would then be YD1, indicating this 30 degree lagging phase shift. This ends the chapter on transformer clock system vector nomenclature.